So, next property we want to check is that if S1 is bigger than S2, then integral S1 is bigger than integral S2. So, let us check that property. So, let us write S1, which is a non-negative simple measurable function, as sigma a I indicator function of a I, and S2 as sigma b j chi of b j, j equal to 1 to m. So, as we had mentioned, whenever you want to do some analysis regarding two simple functions S1 and S2, bring them to a common partition. So, we will write this is also equal to sigma over I 1 to n. S1 can be written as sigma over I, sigma over j 1 to m, a I times indicator function of a I intersection b j. And so, the S1 can be written as this, and we can write S2 as sigma over I, sigma over j 1 to m of b j times the indicator function of a I intersection b j. So, now and union of a I b j intersection b j, j equal to 1 to m union I equal to 1 to n is a partition of x. So, now they have common partitions, and when you say S1 is bigger than S2 means what? So, let us take a point x. So, if x belongs to x, then it belongs to one of a I intersection b j. S1 has the value a I and S2 has the value b j. That means, S1 of x, which is a I, must be bigger than or equal to S2 of x, which is b j on a I intersection b j. So, that means, if this is the representation, so then S1 bigger than S2 implies that a I is bigger than or equal to b j if x belongs to a I intersection b j. Once you observe that, now problem is solved. So, what is integral of S1 d mu? That by definition is sigma over I 1 to n, sigma over j 1 to m of a I, mu of a I intersection b j, and a I is bigger than b j if x belongs to this. So, this is bigger than or equal to sigma I equal to 1 to n, sigma j equal to 1 to m of b j, mu of a I intersection b j, and which is equal to integral of S2 d mu. So, integral of S1 is bigger than integral of S2 if S1 is bigger than or equal to S2. So, that proves the next property. Okay. Now, we are going to look at special functions. If S1 and S2 are non-negative simple measurable functions, then we want to look at S1 V S2 and S1 wedge S2. Recall how was S1 V S2 defined? S1 V S2 was defined as the maximum of S1 and S2, and similarly S1 wedge S2 was defined as the minimum of S1 and S2. So, our and we had shown that if S1 and S2 are non-negative simple measurable functions, then the maximum of S1 and S2 and the minimum of S1 and S2 are also non-negative simple measurable functions. So, we want to check this property now here, that integral of S1 wedge S2 is less than Si integral less than or equal to integral of the maximum. But that is obvious, because if S1 and S2 are simple measurable non-negative simple measurable functions, and you look at S1 wedge S2, S1 wedge S2, that is the minimum of S1 and S2, then clearly S1 wedge S2 is the minimum. So, it is going to be less than or equal to S1 and also going to be less than or equal to S2. And S1 V S2, S1 V S2, the maximum is going to be bigger than S1 and S2 both. So, it is going to be less than or equal to S1 maximum S2. So, what we are saying is S1 wedge S2 is less than or equal to both S 1 and S 2, and both S 1 and S 2 are less than or equal to maximum of S 1 and S 2. And just now, and all are simple functions. So, what we have proved just now, so that will say that the integral of S 1 S 2, the minimum of S 1 and S 2 d mu is less than or integral of S 1, also less than integral of S 2. So, less than or equal to integral S I d mu I equal to 1 and 2, and both these integrals are less than or equal to integral of S 1 wedge S 2 d mu. So, that proves the required property, and that follows from the earlier property on that if S 1 is less than or equal to bigger than or equal to S 2, then integral S 1 is bigger than or equal to integral S 2. And now, let us look at a property. How does this integral behave with respect to limiting operations? So, we want to claim that if S n is a sequence, increasing sequence in L 0 plus. So, it is an increasing sequence of non-negative measurable functions increasing to a simple function S of x, then integral S d mu is limit n going to infinity integral S n d mu. So, this is the first in a sense non-trivial argument required. So, S 1 S n are functions in L 0 plus non-negative simple measurable functions, S n's increasing to S belonging to L plus 0 non-negative simple measurable. We want to show this implies that integral S d mu is equal to limit n going to infinity of integral S n d mu. So, this is what we want to show. So, now let us start observing. So, first, so what is the proof of this? So, note what we are given is S n is increasing to S. Okay. So, that means what? If S n is increasing to S, that means that S n of x is going to be less than S of x for every x belonging to x, right. So, that is obvious from this. If this, then this implies S n is increasing to S, implies each S n x is less than or equal to S of x. Now, S n is a simple function, S is a simple non-negative simple measurable function, S n is less than or equal to this for every n. So, that implies that integral of S n d mu is less than or equal to integral S d mu for every n. So, integral S n d mu is less than or equal to integral S d mu, and integral S n d mu is an increasing sequence of extended non-negative extended real numbers. So, implies that the limit of that which exists may be equal to plus infinity, S n d mu is also less than or equal to integral S d mu. So, here is that a n is a sequence of non-negative extended real numbers, a n less than or equal to a implies a n's are increasing. So, limit of a n will be less than or equal to a. We are in extended real numbers, keep in mind. So, we have proved, so let us call it as 1. So, we have proved in the required equality, we have proved that right hand side limit n going to infinity integral S n d mu is bigger than or equal to integral S d mu. We want to prove the other way around inequality also. So, to do that, here is a small manipulation that we have to do. So, for that what we do is the following. So, let us fix, let a number c between 0 and 1 be fixed. Then c times s of x for any point x, c times s of x is going to be strictly less than s of x. So, here is c times s of x and here is s of x, right. So, let us fix c between 0 and 1 and look at the, and for any point x, let us look at c times s of x. Then the first observation, because c is between 0 and 1, c is strictly less than 1, So, c times s of x will be less than s of x. So, it will be somewhere here. And now, s n x is increasing to s of x. S n x. So, after some stage s n x must be on the right side of c times s of x. So, after some stage it must be on the right side of. So, this is the picture that will happen. So, let us write. So, let us define B n to be the set of all x such that S n of x is bigger than c times s of x. So, collect all those points, right, where this is going to happen, where S n of x is bigger than. See, this stage will depend upon n. So, then now, so that means, so implies that first of all, so let us note that B n plus, if S n x is bigger than c of S n, then S n plus 1 is anyway bigger than S n of x. So, because S n is increasing. So, S n plus 1 x is going to be bigger than. So, B n. So, if so that means this B n is inside B n plus 1 for every n. That means, that is B n is an increasing sequence. So, implies B n is an increasing sequence. Okay. So, that is the first observation, because all B n's S n is increasing. So, if x belongs to B n, then S n x is bigger than c times s of x, right. But S n is increasing. So, S n plus 1 x is going to be bigger than S n of x. So, if S n x is bigger than c times s of x, then S n plus 1 also is going to be bigger. So, x belonging to B n implies x belongs to B n plus 1. That means, B n is a subset of B n plus 1. That means, B n is an increasing sequence of sets. And also observe that each B n is an element in the sigma algebra S, right. Each B n is an element in the sigma algebra S, because B n is where S n is bigger than c times s. All are simple measurable functions, and we have observed that such sets are in the sigma algebra. So, B n is an increasing sequence of sets in the sigma algebra S, and let us observe what is the union of these B n's. So, union of B n's n equal to 1 to infinity. Obviously, it is contained in x, because all are subsets of x, but by the fact that for every x, this picture that we observed here, for every x there is going to be some stage after which S n is going to be bigger than x, because c times S x is strictly less than this. So, that fact implies that this union is equal to x, because, so observation here is, because for every x belonging to x, there is a stage n naught such that S n naught x is bigger than c times s of x, right. That is because S n x is converging to s of x, right, because S n x is going to increase to s of x. So, it has to cross over the this point c times s of x, otherwise it cannot reach that point. Okay. So, B n is an increasing sequence of sets in the sigma algebra, and their union is equal to x, and mu is a measure countable additive, and we had proved a equivalent way of saying that mu countably additive is same as saying whenever a sequence of sets A n is increasing, then mu of A n's must increase to mu of A. So, by that fact, mu of x must be equal to limit n going to infinity mu of B n's. Okay. So, that must be true. So, now let us use all these facts and look at. So, now, so thus, if we look at integral of c times s of x d mu x, if we look at this integral. Okay. So, first of all we claim that this is equal to integral of c times s of x d mu x over B n's. Okay. So, first observation we want to make at that and that is because if we look at this as a measure, right, if we look this as a measure nu of B n, okay, just now we proved integral over sets of simple functions over sets is a measure. So, look at that measure nu and B n is increasing to x. So, nu B n must go to nu of x. So, this fact we are using for, this is the fact we are using for not mu, but we are using for nu, and where what is nu? Nu is integral of C s x over B n. Okay. So, that is the fact we are using here. So, that means this is equal to, so now on B n, what is happening on the set B n? On B n, S n of x is bigger than C times. So, that means C times S of x is less than, so it is less than integral over B n of S n of x d mu x, because that is the definition of the set B n. Okay. So, we have replaced C S x, we are using the fact integral of S 1 is less than integral of S 2 whenever S 1 is less than or equal to integral of whenever S 1 is less than or equal to S 2. So, this is less than or equal to this. Now, B n is a set subset of x. So, this integral I can replace and say that this is less than. So, this is less than, or this is less than or equal to integral over the whole space x S n x d mu x. So, what we are saying is, by this analysis what we have shown is that the integral C times S of x d mu x is less than or equal to this for every n. And because this happens for every n and S n, these integrals are increasing sequence of numbers. So, this implies that integral C times S of x d mu x is also less than or equal to integral over x of s limit. So, is less than or equal to limit n going to infinity of integral S n d mu. Okay. And now, this holds for every c between 0 and 1. So, I can take the limit as c goes to 1. So, implies that integral of s d mu is also less than or equal to integral limit less than or equal to limit n going to infinity of integral S n d mu. So, that is my other way round inequality 2. So, we have proved both ways inequalities 1 and 2. So, 1, if you recall, we had already shown 1 that integral S n d mu is less than integral S d mu, that was 1 we proved, and now we have proved integral S d mu. So, 1 plus 2 imply that integral S d mu is equal to limit n going to infinity integral S n d mu. So, that proves the result, the required result, namely that integral of S n, if S n is increasing sequence in L plus, then you can interchange. So, what is S? That is a limit. So, integral of the limit is equal to limit of the integrals whenever S n is increasing non-negative simple functions. So, it is a nice property for increasing sequences. So, at this stage one can ask the question that we have proved that if S n is an increasing sequence of non-negative simple measurable functions increasing to S, then integral of S n's converge to integral of S. Will this property hold for decreasing sequences? Namely, if S n is decreasing non-negative simple functions decreasing to S, can we say that integral of S n's will decrease to integral S? We do not know that fact at present, we cannot prove at present this fact. Right. In fact, many more properties of such things we will explore as we extend the notion of integral. So, we will stop here today and analyze next time another way of representing integral of non-negative simple measurable functions, and then go over to define integral of non-negative measurable functions. We will extend the notion of integral from non-negative simple measurable functions to non-negative measurable functions. We will do it next lecture. Thank you.